In the previous examples, we have grossly exaggerated the bending that beams undergo. Normally the degree of bending is so small that it is imperceptible. If the stress distribution were superimposed onto a real beam during bending, it might look like this. These arrows show stress values at various locations within this cross-section. The fibers along the top of the beam experience the maximum compressive stress, while the fibers along the bottom experience the maximum tensile stress. To find the total moment that these forces produce about the neutral axis, we add up the contributions of stress from each area of the cross-section. For example, this area dA carries a compressive stress of this amount. This produces a force that acts at a moment arm y to produce a moment. We add up all such contributions by integrating over the cross-sectional area to produce the total moment m acting on this section. A minus sign is added so that a sagging moment can be considered positive. This equation is valid for any distribution of stresses. In elastic conditions, stress can be calculated using Hooke's law, so we can substitute minus E times y over rho into the moment equation. The two negatives cancel out, and we can change y times y to y squared. We can then bring E over rho outside the integral sign, since they do not change from place to place over the cross-section. Now the quantity described by the integral is the moment of inertia. So we can substitute I into the equation to get m equals E times I over rho. This equation allows us to calculate the moment in a beam if we know the modulus of elasticity of its material, the moment of inertia of its cross-section, and its radius of curvature.